Okay, here is a semester test question, a typical modeling question for dynamics modeling. Let's take a little bit of time to read through the question and highlight some important points. So we're told that a decanter can be used to separate immiscible liquids, so that's an important point. These liquids are going to be immiscible. The liquids separate out and float on top of one another in distinct phases, with the most dense phase at the bottom and the least dense phase on top. Right. A company is attempting to develop a new decanter that will separate n phases. Okay, so there's a certain number of these phases that are going to be separated. You have been assigned to develop a model that will predict the levels of the different phases given an online measurement of the flow rates of each phase in the feed line. So we're going to be measuring the flow rates in each phase of the feed line. The decanter will be formed from a vertical pipe section with a circular cross section. So I'm already, if I'm doing this on a piece of paper, I'm already sketching for myself a little picture of what the system looks like. So I'm just looking at this and saying, okay, so there's going to be a feed, and it's going to have n components, and it's going to be coming into some kind of a vertical pipe with a circular cross section, and all of these different layers of liquids are going to be lying one on top of one another. Right, so that's basically what they're saying. Okay, so the decanter will be formed from a vertical pipe. Right, that's what we just did. The model will be used to locate the interfacial point so that the pure liquid can be removed. Okay, so they're talking about these interfacial points over here. So when we are doing this decanting, we're going to want to remove those different liquids. Maybe they are thinking of something like, different pipes that are at certain levels, and they need to be able to locate these ends in such a way so that they know where these intervening levels are. Okay, so each one of these different liquids are going to be forming a cylinder like this. Okay, cool. Right, so let's continue. So this model, right, the liquid levels are measured from the bottom of the decanter to the point between two components. Okay, so they're saying that from the bottom of the container, this will be, what did they say? Li, so that's L1, and that's L2, and that's L3, and so on. So that's up to there, that's up to there, that's up to there, and so on. Right. You may assume that the densities of the liquids are constant and that each liquid, actually just say, so there is a level that's going all the way to whatever the top liquid is, and maybe there's actually air here, and so this last level, so there's a lot of interstitial ones there, and then that will be n. Okay. The liquid. Okay, you may assume that the densities of liquid are constant and that each liquid is removed from the decanter at a rate proportional to the pressure at the bottom of that liquid layer. Remember to keep your analysis general for n components. Okay, so I've got my diagram already partially drawn, so that's the first couple of marks over here. So the first thing we're trying to do is draw a diagram showing your choice of variables. Okay, so I think I've got not a half bad start over here. So we need a name for each of these different phase flow rates. I'm going to call that Fi. So let's continue looking. So we're looking here. They're saying so we know that the liquids are immiscible, so they'll all come in the same pipe. maybe there'll be some kind of a baffle over here that'll stop it'll break up, and so here there'll be little disaggregation zone, and then we'll have a nice set of perfectly separated out liquids settling out over on the right hand side. So liquid comes in here, goes, and then settles out. It's almost like salt, vinegar, and olive oil that you shake up, and you have the layers forming. So we've got a flow rate of Fi. Let's see if they specify units. So they say the liquid separate out, so they just say that we have a measurement of the flow rates of each phase in the feed line. So we'll just assume, I think to make things easy, that these are volumetric flow rates. So if I were modeling this, I would do something like, okay, so N is the number of components. Let's say the most dense first. So if I is something like cubic meters per hour of component I, rho I is the density of component I. I suppose actually it's a bit of a bad habit to use units instead of the actual values, and so I think it's a better idea to flow rate, just say flow rate. Right, and then we've got these L's. And so now I think if we probably also need to introduce a couple of additional auxiliary symbols, you know, so we have something like MV1 and M1. So we'll say something like VI is the volume of component I. Mi is the mass. Now I'm going to introduce a different symbol over here, saying something like HI. Right, so HI is the height of the ith component fraction. So that's going to be just this, that's going to be this little piece of the slice, right? Because they're telling us that we have levels that are measured from the bottom all the way to the top. But if we think about calculating a volume of that component, we're going to need the difference between subsequent levels of these interficial components that do this relationship. Right, so I think that's pretty much the symbols all sorted out. And we probably also need a couple of additional symbols just for the area. So let's say these are all, so that's the area. Of the tank. And we probably need some kind of F out for each one of these components. And that will be Okay, so they have, okay, wait, there's a very important thing that they've added here. So you may assume that the densities of liquids are constant and that each liquid is removed from the decanter at a rate proportional to the pressure at the bottom of that liquid layer. Okay, that's a very important given. I'm just going to highlight that for myself. That's removed at a rate proportional to the pressure at the bottom of that liquid layer. Okay, so let's start writing down equations. So I think we're basically done with this. And now we're going to start writing down the model equations over here. Okay, and we're going to check that this is correctly specified. So I'm going to let's move this over here. So we're going to do our standard modeling thing, and let's just keep the diagram in play over here. And so, okay, let's start. So we've got our first couple of equations. I think we always start with what are the balances that we can do, right? So are we going to do a component balance? Yes. Are we going to do a total mass balance? I think if we only do the component balances, because these things are immiscible, that'll be enough. Nothing's being said about temperatures or anything like that, so I think I'm just going to do n component balances. They also ask for it to be general in terms of the amount of stuff that we're doing, so I think I'm just going to keep it like that. And so assuming as well that these are, actually we should actually maybe just say this is also a volumetric flow rate. And so now that we've got all our symbols defined, the mass balances are relatively easy to do. So we're going to have dmi dt, and now notice I'm just going to say dmi because we know that there's going to be 5 of them, or there's going to be n of them. So that's going to be assuming that we know fi. Right, so we said that we knew how much of each component was coming in, and so we're going to say fi is going to be what's going to come in with density rho I, and f out with density rho out. Okay, so minus rho I f out I. Okay, and there's going to be n of those equations. I'm just going to put a little note here of like how many of these things we are counting. And so let's build out a table, so we can say these are our equations, and this is the number of equations, and then inputs, parameters, right? So we have our inputs here are fi, and I'll just to be sure, because of this given over here, so because they've told us that the liquid is removed from the decanter at a rate proportional to the pressure at the bottom of that liquid layer, how this would happen mechanically is if each one of these little straw things was kind of coming around and going out at the bottom over there, so that there's a siphon effect, and so you can kind of see the driving force is going to be the pressure that is above that point. So if there's a certain amount of liquid over there, there's going to be a pressure of rho th over there, and that'll push liquid out through that straw or whatever is being used to remove this. An important point to see here is that as we go down this liquid column, the pressure increases, but the pressure at the bottom of this component is actually that pressure plus that pressure plus that pressure plus, and so on. And so each time we have a pressure, that's actually not a bad thing to add. We should have some kind of a way of referring to that pressure. So let's say that we've got a pressure. So we say pressure 1, pressure 2, pressure 3, and so on, and then that will be so that'll be 1, 2, 3, 4, and so on, all the way up to pressure n. but remember, so this will be at the bottom of, so that'll actually be Pn over there. So that'll be the pressure at the bottom of the column, right? So because there are I components, so this pressure over here, the interface over there, that'll be the bottom of that, the bottom of that, the bottom of that, and so on. Okay, so L1 is measured to the top of there, but the pressure is measured at the bottom there. Okay, and so we probably want to add that to our list of symbols. We can say that's in pascals. Okay, so let's get back to this. Okay, so we've got our equations. We've got our first mass balance equation for one, or component balance, one for each component. So the inputs here are Fi. Parameters are rho I, because we're told that they don't change. And the outputs are Mi and F out I. Right. And I think those are the only dynamic equations that we're going to have. Okay, so we have n of those equations, and then I'm just going to kind of count here. So we'll have n of these inputs over here, we'll have n of these, and we have effectively 2n outputs contributed over here. Right. Next set of equations, I think the next one is the one that we've just been speaking of, which is that the pressure at the bottom of every component is going to be the density times gravity times h of I. So that's the pressure contributed by that component. But remember, to get to the bottom of the component, we're going to have to sum these quantities. So we either have to do something like the sum of that over for I going to n. I think that's the easiest way. Sorry, not going to, yes. So let's say we get this sum notation right. So it'll be something like rho j, hj, for j going from I to n. Okay, so that'll be, in other words, so if I'm working with the first one over here, I'm going to sum up all of them, but if I'm working with that last one, it'll just be from there to n. So just that last one. So that looks pretty good. So that'll be the pressure at the bottom of each one of these things, and that'll refer to h. And remember, we said h is going to be the height of each of those individual ones. Now we have one of these for every one of the components. So let's count here again. Okay, we don't have any inputs. We have parameters. We've got the rows that we've already counted. G is a parameter that's always going to be constant. We've got the outputs are going to be here pi, just to be clear that that's not a row. Pi and pi and hi, and so there will be another 2n of those. Then of course we need equations for h, so we know that hi is going to be the difference between the corresponding L's, right? And so if we define L0 as let's just add something here, saying something like L0 is equal to 0. And that's an L. So we've got L0 is equal to 0, and that gives us another parameter just to introduce a new symbol, but then we can easily define these L's as being the H's as being Li minus Li minus 1. Okay, so those there are again, n of these. Now we could have done this slightly differently. We could have had n minus one of these and not introduced L0, because then we would have just had H1 is equal to L1 as an equation. Okay, so but it all comes out in the wash. It's all the same. Right, so we've got again, these L's are also outputs. We haven't counted them yet, so that would be Li, and there's n of them, and there's one of these. Right. Okay, and we've got one of these equations over here. So let's continue. The next couple of equations I want is the geometry. We also probably want to relate the volumes to the masses. So Mi is equal to Vi times rho I. There'll be n of those. Again, all outputs. We've counted m before, we've not counted V before, so Vi. There'll be n of them. So the next equation, so we've got relationship between the mass and the density and the volume. We've got the levels. So I think we're almost done. Let's see. Oh, okay, and then obviously we've got Vi is equal to A times HI. Again, there'll be n of those. Our outputs, we've counted Vi before, we haven't counted A, and we've counted HI. Okay, this is actually starting to look pretty good. Then the last, we also have F out. I is equal to what they said. We've got the proportionality constant. So some proportionality constant, I suppose we can give each level its own proportionality constant, but they said that's proportional to the pressure at the bottom. We've already got that pressure at the bottom, so that's going to be satisfying this. Each liquid is removed from the decanter at a rate proportional to the pressure. So this here is tracking this. Okay, so we've got a mass balance, we've got a way to calculate the pressure, we've got the level, the relationship of these measured levels to the actual height of the component itself. We've got the mass density relationship, we've got geometry, and we've got the outflow relationship. So I think we're basically done. So let's start counting. Let's just do the housekeeping here. So we've got n of these. F out we've already counted. Okay, so this is already there. K is there. P is there. Okay, so we're just gonna check go through one check over here. So Mi, yes. Rho I, yes. Fi, yes. Rho I, yes. F out, yes. We've got Pi, yes. We've got rho J, which is that same J. We've counted G. We've got H. That H is the first time that we see H, yes. So here we've got these. We've only got the levels. We've got L0. So you add an equation, add a parameter. We've got no, actually, you know what? We can't count that as an equation if we're doing it as a parameter, so I'm just going to cross that out. So we're just going to add L0 as a parameter. So we've got Mi, we've got Vi tracking, yes, Vi, the H is already there, F out is already there, Ki is here, so those are tracking. Pi is already there. Okay, cool. So let's count. So we're going to count 1, 2, 3, 4, 5, 6 in equations. We're going to count n inputs. We're going to count n plus 1, 2, 3 plus n is 2n plus 3. Parameters. You know what? Yeah, this L0 is causing me trouble because this, I haven't counted it as an output over there. So actually, let's call we'll see how the degrees of freedom work out. So we've got 2n plus 3 over there, then we've got 2n, 4n, 5n, 6n outputs. Right, okay, that's looking pretty good. Okay, and now the last piece of the question. Okay, so we've got our equations. Verify that we've got the last piece of the question here is we've done this. Now we have to verify that the simulation problem is correctly specified. What is the simulation problem? The simulation problem is inputs and parameters given and outputs. So outputs must be equal to equations. So let's go to our degrees of freedom analysis, and indeed, yes. Okay, so but we have to write that down. So we have to say, okay, simulation. Okay, outputs and parameters given for the DOF. No, wait, outputs. Inputs and parameters given for the degree of freedom. The outputs must be equal to the equations. Okay, so DOF is equal to equations minus outputs is equal to 6n minus 6n equals 0 equals win. Okay, right, there you go. It looks like we have a winner.